All right, so we have previously learned how to name ionic compounds, both binary ionic compounds, we just have two things, and also things with polyatomic ions, including oxyanions. And we'll need to know our oxyanion names for some of our acid namings. We also talked about molecular compounds, where we just have nonmetals. We only do binary molecular compounds, which is great for us because it gets more complicated when you have more than two things. So now on to our last category, naming acids. So acids are a type of molecular compound, meaning that they're just nonmetals, and they form ions when they dissolve in water. So if you put an acid into water, it dissolves and it forms ions, which is not what molecular compounds normally do. So this sets them apart from other molecular compounds. How we can tell if something's an acid, if we're looking at the formula, hydrogen comes first. That's a rule for this class. It's not always true everywhere else. So we'll have hydrogen first. We can have more than one hydrogen. It can be H, it could be H2, could be H3. It just depends on what the acid is. And that's going to be followed by one or more nonmetals. It might be a polyatomic group. We can categorize our acids into basic groups, and we've got different naming conventions for those. We've got binary acids. Again, binary here meaning two things. So we've got hydrogen and something else. Just one other thing typically. You can have like polyatomic ions that are there that still follow the binary naming convention, but that's just part of the fun of chemistry as we get to break rules that we just established. We also have oxyacids, and our oxyacids contain a nonmetal and oxygen, aka an oxyanion. Again, these will have hydrogen up front. Now, if we're starting from a name and going to a formula, there's a dead giveaway in the name. The name always contains the word. Any guesses? All of you 100% of the time would be able to recognize that it's an acid based on the name because it contains the word acid. Dead giveaway. Couldn't be any easier. So if we're starting from the name, going to the formula, acid in the name lets you know that it's an acid. So that's kind of cool. So jumping into binary acids first. Our binary acids are composed of hydrogen. Hydrogen comes first. And a nonmetal. So we'll have exactly two elements. Again, sometimes we have more than two elements and we still name it with the binary convention. That's just the fun. Our formula is we have hydro in front. So this in red is the formula part. All of our binary acids are going to start with hydro. We're going to change the ending to ic and add the word acid at the end. We've got some examples. So HCl, we've got an H in front, so we know it's an acid. It's just two things, so it's a binary acid. We give it the hydro prefix. We take the base for chlorine. So drop the ene, so it's chlor. Change the ending to ic and add acid. It's the same idea for HBr. Bromine is our nonmetal in this case. That's not hydrogen. And so we drop the ine ending. So the base is brom. Change the ending to ic, add acid. Since it's binary, we've got the hydro prefix. It's very important that you have the hydro prefix on there, as I'll hopefully remember to show you. All right, so naming some binary acids. It's, again, not always just one hydrogen in front. We can have more than one hydrogen. The idea is that we only have two elements. So HF is our first binary acid that we'll name. How do we know it's an acid? It's got hydrogen in front. Hydrogen in front means it's an acid. That identifies it as an acid. The snarky answer would be, well, it says naming binary acids at the top, so of course it's going to be an acid. So it's an acid, and it's also a binary acid because we have exactly two elements. Our rule for binary acids is that we have to have the hydro prefix. So we have hydro at the front. Our other thing that's not hydrogen is fluorine. The base for fluorine we drop the INE to get fluor, not flour, fluor, as our base, and then we change the ending to ic and add acid. So we get hydrofluoric acid, made famous in the hit TV show Breaking Bad. It's great for dissolving bathtubs. Questions about that? Okay, then we've got H2SE. What kind of thing is H2SE? Ionic molecular acid. It's okay, you can be brave. Great, good collective thinking. Yes, it is an acid. It's an acid because it has hydrogen. What kind of acid is it? It doesn't have oxygen in it. It's not an oxyacid. We just have two elements. It's a binary acid. Part of the reason I'm talking through and trying to get you to think about what kind of thing it is so that we can build this framework for this choose your own adventure of how do we name it, which convention do we use. So thinking about what kind of chemical it is, and then what kind of that chemical is it? Is it ionic molecular acid? And then which of the groups does it fall into for that? So this is a binary acid because it's just two things. And our base, our non-hydrogen thing, is selenium. And so we drop the IUM at the end. Since this is a binary acid, we use the hydro prefix. Our base for selenium is selen. We change the ending to ic and add the word acid at the end, hydroselenic acid. Does anyone know why we have two hydrogens instead of one hydrogen? I'm terrible at reading lips, but I think I understood what you were saying. So we want to look at selenium. Selenium is Se on our periodic table. Find selenium. It's under oxygen. What's the charge going to be if selenium forms an ion? 2 negative, because it's 2 spaces over from our noble gases. So it's 2 negative. In order for us to balance that charge out with hydrogen, we would need 2 hydrogens. And so that's why we've got 2 hydrogens. That's why it's H2SE. It's so that the charges balance out. Any questions about binary acids? Yes?
Why is it that we don't use like any prefixes or anything if there's like a set amount?
We don't need to specify. We don't need to specify how many hydrogens we have because we know what the charge is on selenium. It's always the same thing every single time. So we can figure out through deduction that we're going to have 2 hydrogens. And most chemists should be able to do this almost instantaneously, because we would have done it a lot to get to be, calling ourselves a chemist. And once you get good at it, even modestly good at it, it should be relatively quick for you too. Okay, so oxyacids are our other type of acids. Oxyacids are acids that contain oxyanions. Oxyanions always end in ate or ite. That's one of our indicators that we're dealing with an oxyanion. These are the only endings for oxyanions. So anytime you see ate or ite, you know that it's an oxyanion. There's lots and lots and lots and lots and lots of oxyanions. So again, it's easiest if you remember, if you memorize, or if you look up the ATE ending and you know how we're going to change things. So let's look at some oxyacids. We've got HNO3. It's got an H in front, so we know it's an we know it's an acid. It's got NO3 after that, so we know it's an oxyacid. And the NO3 has the nitrate ion. NO3 minus is nitrate. H2SO3, we've got hydrogen in front, letting us know that it's an acid. SO3 has oxygen in it. It's an oxyanion. This is the sulfite ion, the ITE ending letting us know it's 1 fewer oxygens than our 8 form. It's still a 2 minus, just like sulfate, which we can see down below. It's still a 2 minus, and because it's a 2 minus, we need 2 hydrogens in front to balance the charge. So again, we're balancing our charge with the correct number of hydrogens. And then H2SO4, we've got 2 hydrogens in front, again, because the sulfate ion has the 2 minus charge. The number of H plus ions depends on the charge of the oxy anion. So for example, with phosphate, it's got a 3 negative charge. So if we take H plus, PO4 3 minus, you can either just look at it and do the math in your head, or we can crisscross it, and we'll see that we need 3 H's to balance out the 3 negative charge. So it would be H3 PO4, for example. So for naming oxyacids, we've got 2 possible rules, and it's based on the ending, only the ending of our oxy anion. So we're going to take the base name of our oxy anion, just the name of our oxy anion. If it ends in ate, it turns into ic. If it ends in ite, it turns into ous. So ate, arrow, arrow, turns into ic. Ite turns into ous. You may remember that we can also have prefixes for our oxy anions. The prefixes stay on during nomenclature. We don't adjust them or change them in any way. We just change the ate or the ite to ic or us. And you just have to memorize those changes. So really the hard part, I think, about oxyacids is remembering the oxyanion names. For now, it's reasonably okay for you to just use your green sheet, refer to the ATE ending box at the top, and then if you need to, also refer to the table below that on your green sheet that tells you what to do if you add 1, subtract 2 oxygens. But I would recommend memorizing those ATE endings because you'll need to know them for our ion quiz. Okay, so naming oxyacids. We've got 2 examples here. We've got HNO3. We know that HNO3 is an acid. We know it's an acid because it has H in front. H in front means it's an acid. It's not a binary acid because we've got more than 2 elements. We've got NO3 coming after our H plus at the front. And so we find what looks like NO3. We would either look it up or we would search our brain. What would be the oxyanion that's like NO3? It's NO3 minus. You could also figure out it's a 1 minus charge because we've got 1 hydrogen in front. So we would rack our brains and think, what is this? It's nitrate. Okay, so we've got the acid with nitrate. We have to remember our rule. How do we change ATE? ATE turns into ic. So this is nitric acid. We have another example with H2SO3. We know that it's an acid because it starts with H. So we've got an acid, and so we would be looking for something that looks like SO3. We could figure out it's a 2 minus because we've got 2 H's in the front. So we'd find on our green sheet something that looks like SO3. We would find SO4, 2 minus. SO4, 2 minus is sulfate, and we have SO3, 2 minus. How does our name change when we go from 4 oxygens to 3 oxygens? We dropped 1, so we changed the ending to ITE. So this is sulfite. So the ITE ending comes into play, and we've got the oxyacid with that, so we're going to change the ending to what? OUS. So ite turns into OUS, and then we also do this fun thing. We add UR for some reason, so it's sulfurous acid. Isn't that so fun? There's a similar thing that happens with phosphate, where instead of phosphic acid, it's phosphorus or phosphoric acid for phosphate. If you forget to do that, guess what? A chemist will still understand it. So it's not that big of a deal. Try to remember to add UR back in, or in the case of like phosphate, the OR. I'll write it out because I'm talking. So if we make H3PO4, this is the oxyacid made with phosphate. The ATE ending turns into ic. But we also do this fun thing where we add in OR. So it's phosphoric acid. I don't know why, that's just what we do. Again, if you write phosphic acid, chemists will understand. Did we have any questions about oxyacids? I'm going to give you some time to try naming these oxyacids. All right. We've got some oxyacids to name. First up, we've got HNO2. How do we know HNO2 is an acid? It's got H in front. Bingo. H in front means it's an acid. And then the other part is NO2. We could also deduce that it's a 1 minus charge. If we didn't know what this was off the top of our head, we would find something that looks like it on our green sheet or somewhere else, and we would find NO3 minus, and that's nitrate. We have 2 oxygens, however. So this is nitrite. So we're making an oxyacid with nitrite. We're going to change the ending, the ITE ending. And that ending change is to OUS. ITE turns into OUS, and we add acid to the end. So this would be nitrous acid. Then we've got HClO4. HClO4 is an acid because it's got H in front. And then we would find something that looks like ClO4 minus. We've got ClO3 minus on our green sheet. This is our 8 ending, our chlorate. We've got 1 extra oxygen. We've got ClO4 minus. And the change that we do for that is we add per at the front. So this is perchlorate. So this turns into perchlor. How does the ending change? It's gross. Ic acid. So this is perchloric acid. So again, the prefix doesn't change. We just leave it on there. All that we change is the ending. Questions? Okay. There is, in the online book, this big nomenclature flowchart that you can refer to. It's obviously also here, so you could come back to it here. This is basically just help you choose your own way through figuring out what we have. So we've got ionic compounds, molecules or molecular compounds, and we've got acids as our 3 main categories. For molecular compounds, we just run it through add the prefix machine and change the ending to "ide." For our ionic compounds, it kind of depends on what our cation is, what our positively charged part is. And there's also some stuff that can happen with polyatomic ions, but it's mostly just the same thing. And then we just talked about the acids part. It's either an oxyanion as the negatively charged part, or it's a monoatomic ion, and so we've got a binary ion. I like the flowchart that's in Nivaldo Turo's Introductory General Chemistry, I think is the book. You could probably find a picture of it online. I prefer that one. And then this is the last slide, just putting all of our nomenclature knowledge together. So I'm going to give you some time to try these. Feel free to discuss with your neighbors. And then we'll come back together. Okay, that was 5 minutes-ish. So the following chemicals. We've got PCl3. What kind of compound is PCl3? Is it ionic, molecular, or acid? We know that it's not an acid because it doesn't start with H. All right, so our options are ionic or molecular. Ionic compounds have metals in them. Phosphorus and chlorine are both nonmetals, so we don't have a metal, meaning that it's molecular. So this one's molecular because it's nonmetals only. It's also binary. So we're going to use our molecular naming convention. Molecular is when we use the prefixes for the number of things that we have. So the first thing that we have is phosphorus. We've got one of them. Our prefix would be mono, but it's the first thing, so we omit the mono prefix. So this would be phosphorus. And then we've got 3 chlorines. So we're going to use our prefix for 3, which is tri. And then we're going to use the base for chlorine, which is chlor. And we change the ending to IDE. So this would be phosphorus trichloride. Next one up, we've got HClO4. What kind of compound is HClO4? It's an acid. We know it's an acid because it's got H in front. What kind of acid is it? Is it binary or oxyacid? It's an oxyacid. We know it's an oxyacid because there's oxygen. It's also not just 2 things. We've got ClO. So ClO is our oxyanion. We would need to figure out what is ClO minus. So we'd find something that looks like ClO minus, or think of something that looks like ClO minus. We'd get ClO3 minus. That's our 8 ending. So this is chlorate. If we went down to ClO2 minus, that would be the ite ending. So that'd be chlorite. We've lost one more oxygen than that. We've got just ClO minus. And so we also have to add a prefix. We add the hypo prefix. So it says hypochlorite. And then when we make it an acid, we change the ending. So we change the ITE ending. Ite turns into us. So this is hypochlor, change the ending to OUS, add acid. So hypochlorous acid. Then we've got CaOH2. What kind of compound is CaOH2? Is it ionic, molecular, or acid? We can rule out acid right away, right? Because it doesn't have a hydrogen in front. No hydrogen in front. Can't be an acid. So we've got ionic or molecular. Molecular is all nonmetals. What kind of thing is calcium? Where do we find it on the periodic table? Ca. It's way over on the left side, right? It's in our second column, our second group. What's the name for that group? Does anyone remember? It's our alkaline earth metals. So it's a metal. It's also, on the left side of the periodic table, so it's a metal. Since we've got a metal, that means it's ionic. It's a mix of metals and nonmetals. How many charge options do we have for calcium? Is it always going to be the same thing, or does it have multiple options? Perhaps a better question, what's the charge on calcium when it forms an ion? It's in the second column. When it forms an ion, it's going to form an ion that has the same number of electrons as the nearest noble gas, which is argon, which has 18. So to go over 2 spots to the left to wrap around to get to argon, that represents losing 2 electrons. It's also in our group 2A, so it's always going to form a 2+ charge. Since we know that it's Ca2+, and it only forms that one charge, we can just write calcium for the calcium part. And then we need to know what's the name of the OH group. It's one of our polyatomic ions. Yeah, it's hydroxide. So the name for this is just the name of the 2 different ions put next to each other, calcium hydroxide. And then we've got Ni3PO42, which has a whole lot of stuff going on. What kind of compound is Ni3PO42? It's not an acid because we don't have H in front, so it's either molecular or ionic. You can probably guess that it's ionic because we've got more than 2 things. We could also find Ni on our periodic table, nickel. Right, nickel, Ni, is one of our transition metals. So it's a metal. And so it's ionic. So then we have to ask ourselves, what's the charge on nickel? Based on where it is on the periodic table, given that it's a transition metal, it's in that rectangular block in the middle, and it's not zinc or silver, we don't know. We just shrug our shoulders. I don't know. Could be a number of different things. So we will have to figure out what it is in this particular context. What we can do to start is write that it's nickel, because we know for sure that it's nickel. We don't know the charge. We would have to specify the charge when we write the name. That's where the Roman numerals in the parentheses come into play. So we can start by writing the name and then leave a little space in those parentheses that we'll have to fill in at some point. Leave a little space after we're going to put the charge. And we can move on and work on the oxyanion, the PO4. So we'd have to know what PO4 is and what charge it has. Who knows what PO4 is? Phosphate. So we find PO4, it's phosphate. So this is going to be nickel something phosphate. Phosphate is PO4 3-. How many PO4 3- do we have? We've got 2 of them, right? So our total charge from our phosphates is 6-. Every ionic compound is going to have a neutral formula. We know also that it's neutral because it doesn't have a charge in the top right corner. So this whole thing is neutral. That means that the positive charge from the nickel must balance out, counteract the negative charge from the phosphate. So we've got nickel with some positive charge. We've got 3 of them, and we know that the charge is whatever X plus is. So 3 of them, they all have the same charge of some value, and it has to balance out 6-. So it's balancing out with a 6+. So 6+ equals 3 times whatever the charge of the nickel is. So the charge of the nickel is going to have to be 2. So it's nickel 2 phosphate. And then last but not least, we've got HF. What kind of chemical is HF? It's an acid. We know it's an acid because that H in front. And then we can figure out it's a binary acid. And binary acid means that we have hydro at the front, then the base, and we change the ending to ic, and we add the word acid at the end. So this is hydrofluoric acid. Did we have questions about any of those? Yes?
For C and D, why does the two subscript not matter in naming? Is that because they're ionic?
So for C and D, because they're ionic and because the subscripts are based on the charge, we can figure out the charge from the name. So we take the name, figure out what the individual parts are, crisscross them or swap and drop them to get the charges to balance, and we would come up with those subscripts. So the idea behind our very particular naming convention, this is the one that everyone all over the world uses if they're doing chemistry. The idea behind the very particular naming convention is that you can go both ways. You can go from the formula to the name, you can get from the name to the formula, and you're only ever going to move between those two that name and that formula. It's always referring to exactly one specific thing. So we have to be really exact. There's like a billion chemicals that you could possibly make. So we have to make sure that our naming is precise enough to call out exactly one thing. And I mentioned that I wanted to show you why that hydro prefix is important. So let's imagine that we've got HNO3 and we've got an acid that's just a binary with nitrogen. We already did HNO3. NO3 minus is nitrate. So this would be nitric acid. Our binary naming convention means that we have to add hydro. Let's see what happens if we don't add hydro. So for binary acids, we use the base of the nonmetal that's not hydrogen. So it's be NITR. And we would change the ending to ic and add acid. So if we don't have a hydro prefix, we cannot tell these two apart, and that is a problem. And so that's why we have the hydro prefix. We have the hydro so that we can distinguish between HNO3 and H3N. Those are two very different chemicals. Bad things might happen if you used one instead of the other. That's why we have the hydro prefix, in case anyone was wondering. Any questions at all about this chapter? Okay.